Okay, this is chapter 7. We're still talking about basic algebra, and we're going to be discussing section 3, which is solving simple equations. Linear equations are basically equations that if you graph them, they would make a straight line. Also, they only have usually whatever their variable is raised to the first power, like x. Usually we have an x in it, raised to the first power. So today we're going to be solving linear equations in one unknown, and solve their formulas. So when we talk about equations, an arithmetic equation such as 3 plus 2 equals 5 means that the number named on the left, 3 plus 2, is exactly the same as the number named on the right, 5. An algebraic equation such as x plus 3 is equal to 7 is a statement that the sum of some number x and 3 is equal to 7. If we choose the correct value for x, the number x plus 3 will be equal to 7. X is just a variable, a symbol that stands for a number in an equation. It's a blank space to be filled. Many numbers might be put in that space, but only one number or only one makes sense in the equation to make it a true statement. Each value of the variable that makes an equation true is called a solution to the equation. So the solution of x plus 3 is equal to 7 is x equals 4, because when we take 4 and we plug it in, we take 4 and we plug it in where x was. So in other words, if we left this blank right here, left the space blank for x, and they tell us that x equals 4, and we plug that 4 in there. Then we check to see if it's true. 4 plus 3 is 7, and 7 is equal to what it's supposed to be, 7, so that is true. So 4 is a solution to that equation. So in this one, we've got 2. I'm going to put blanks where there are x's. They're telling me to plug in, let x equal 3 in those blanks. So I'm going to put a 3 here in both of these blanks. Then I'm going to go to my calculator and I'm going to type in 2 times 3 minus 9. Well, 2 times 3 minus 9 is negative 3. I'm going to go to my calculator again and type in 18 minus 7 times 3, and that's going to give me negative 3. Because these are both equal to each other, x equals 3 is a solution to this equation. 2x minus 9 equals 18 minus 7x. Okay, the equation x squared plus 6 is equal to 5x is true for x equals 2. So I'm going to take the same equation, and wherever I see an x, I'm going to put blanks, because that means that they want me to be able to plug in something for that x. The something that they're wanting me to plug in is 2. So I'm going to go plug in my 2's, and I'm going to type in my calculator 2 squared plus 6. That's going to give me 10. And then I'm going to type in 5 times 2, which also is 10, which verifies the fact that 2 is a solution to our original equation. Okay, now this one is tricky because this one has 2 solutions. They asked me, okay, well now try x is 3 in that same equation. So if I try 3 squared is 9, and 9 plus 6 is 15. 5 times 3 is 15. Okay, so that's true. So actually this equation is called quadratic. It's not linear, but because it has an x squared, it makes if we were to graph it, it would make a U. Okay, so on the graph, it makes sense that it would have 2 answers because it has 2 places across from itself that would give you the same value for that y. Okay, which I don't expect you to understand all of this, but this is why that happens. Okay, so both of those, 2 and 3, actually work for that equation. Equations with the exact same solution are called equivalent equations. The equations 2x plus 7 equals 13 and 3x equals 9 are equivalent because substituting the value 3 for x makes them both true. We can say that an equation with the variable x is solved if it can be put in the form x equals something, where this something is some number. Some simple equations are easy to solve by guessing, but guessing is not a very dependable way to do mathematics. We need some sort of rule that will enable us to rewrite the equation to be solved as an equivalent solution. The general rule is to treat every equation as a balance of two sides. Any changes made in the equation must not disturb the balance. Any operation on one side of the equation, and we're talking about when we say one side of the equal sign, must also be performed on the other side. Two kinds of balancing operations may be used. Adding or subtracting a number on both sides of the equation does not change the balance. Also, if we multiply or divide on both sides of the equation by a number not equal to 0, that's not going to change the balance. So those are something that you're able to do. The trick to solving an equation is to choose the balancing operation or operations that will isolate the variable only on one side of the equation. So, step 1, it says we want to change this we want to change the equation to an equivalent equation with only x on the left. Okay, so let's talk about, I'm going to write this up here. So most of you, this is kind of what this was talking about earlier, but most of you are kind of able to brainstorm. Well, what number minus 4 is going to give me 2, right? You kind of know that. But they're not going to always be this easy. So this is one of the ones we want to kind of start out with. So the first thing we want to do is go to the side of the equation that has our x on it. And we want to get rid of the thing that's not connected to the x, which is our minus 4. So how do you get rid of a minus 4? You do the opposite of whatever's happening. So if we're subtracting here, to get rid of the minus 4, we would want to add 4 on both sides of our equal sign. That way it stays balanced. Whatever we do to one side, we're doing to the other side. So in this problem, you would just bring your x down. You would say negative 4 plus 4 is nothing. And then you would do 2 plus 4, which is 6. And so the answer would be x equals 6. If we plug in 6 here for x, 6 minus 4 gets us 2. So we know that that is the right answer. Solution. When adding or subtracting numbers on both sides of the equation, you may find it easier to show the work underneath the original equation. Here's what this would look like, which is what I just did, except for I just didn't write the 0 down. Okay. Notice that to solve these equations, we always do the opposite of whatever the operation is being performed on the variable. If a number is being added to x in the equation, we must subtract the number in order to solve. If a number is being subtracted from x in the equation, we need to add that number in order to solve. Finally, whatever we do to one side of the equation, we must also do to the other side. In the equations solved so far, we need to add or subtract to solve because numbers are added or subtracted from the variable. In some equations, the variable may be multiplied or divided by the number. To solve such an equation, do the opposite of the one being performed on the variable. Be sure to perform the same operation on both sides of the equation. So, to solve this equation, 27 minus 3x, 27 equals negative 3x. We're going to go to the side of the equation that has the x on it, and since it is negative 3 times x, to get rid of it, we would need to divide both sides by negative 3. Okay, negative 3 divided by negative 3 cancels out because it turns into 1. So we end up on this side just having x, and 27 divided by -3 ends up being -9. So if we plug in -9 into our equation, -3 times -9, we would get back our 27 that we started with. Okay, this time we're saying x divided by 3 is equal to 13. So to get rid of a divided by, you want to multiply by 3 on both sides, because the opposite of dividing is multiplying. So these 3's would cancel out, and we would get 13 times 3, which is 39. They cancel out because they turn into 1. 3 divided by 3, those are going to turn into 1. And then 13 times 3 is going to be 39. If we plug 39 back into our original equation right here, and we say, well, what is 39 divided by 3? We would get 13. So you're always able to kind of check yourself. This one could be a little bit tricky. So when it's written like this, what I like to do is rewrite it and put the negative on the bottom with the 4. Because then I know I can multiply both sides by -4, because it's x divided by -4 I want to multiply. Well, these are going to turn into 1, and I would get 5 times -4 is -20. And so if I plug -20 back in here, I would have -20 on the top. And remember, we move the negative down here with the 4. So -20 divided by -4 is 5, which is correct. When a negative sign precedes a fraction, we may move it either to the numerator or denominator, but not to both. In the previous problem, we placed the negative sign in the numerator, and I worked it, the way that they've got it up there, they placed it in the numerator, and when I worked it, I put it in the denominator. It's just another way to do it, whichever way you feel more comfortable. But you can't put, this is basically saying you cannot put a negative on the top and the bottom. That wouldn't make it true if there was just one negative there. Okay, the capacity of a conveyor belt in metric tons per hour is given by this formula. C equals 3.6 SDA. S is the belt speed in meters per second. D is the density of the load material in kilograms per cubic meter. A is the cross-sectional area of the load in square meters. Suppose that a certain load material has a density of 750. So I know now that I'm supposed to plug this in for my density. A cross-sectional area of 0.083 square meters. Well, it says that the cross-sectional area should get plugged in for A. And what it's asking us, what is the speed? So we're solving for S. What is the speed needed to move 1,000 metric tons per hour? So C is the capacity of a conveyor belt. So we're trying to find out S, which is the belt speed in meters per second. So I know C, so I'm filling in this stuff right here. C equals 3.6 SDA. Well, C was my capacity, which they told me is 1,000 metric tons per hour. And that's supposed to be equal to 3.6 times S. Well, S, we don't know. That was our speed. So I'm just going to write S down. And then times D, and they told us D is the density, which in this problem we're going to get 7, so times 750. I'm going to put this there to kind of separate this. I'm also going to put a line through this S so it doesn't look like a 5. And then times A in my formula would be the last thing that I need to do. And we know that A is our cross-sectional area of 0.083. So 0.083. Now, what I need to do is I need to multiply 3.6 times 750 times 0.083. These three numbers right here, I need to multiply them so I can kind of reduce this down so I can solve it. So 1,000 equals, I don't know what S is still, but I can do 3.6 times 750 times 0.083. Okay, and when I multiply that 3.6 times 750 times 0.083, I'm coming up with 224.1 times S. And so now I'm going to kind of move this over here so you can see it a little bit better. But I've got 1,000 equals 224.1 S. We're going to want to divide that 224.1 on both sides of our equal sign. Okay, so that's going to get me S is equal to 1,000 divided by 224.1. Okay, and so I have to round on this one. The numbers involved in the problem, I've got two significant digits. This one only has one. I think I'm going to go by the main one in the problem, which is two significant digits. So I would think that they probably want you to round to 2 decimal places. So I'm going to say 4.5 because it was 4.46. So 4.5, and that answers my question of the belt speed in meters per second. So we're going to get 4.5 meters per second. Okay. Now, on this last part, they kind of worked it out for you again, and look, they rounded to 4.5. Okay, so meters per second. I'm going to put another video up on section on 7.3, just that goes over some more problems of these basic add, subtract, multiply, or divide early algebra problems. If you're struggling with this and still not understanding, I would definitely watch that.